We will start with the fundamental concepts. The focus of this course is not about teaching you how to use all these tools, as you are probably capable of using them already. This course wants to explain how these models works and what are the extraordinary engineering works like OpenAI, Anthropic, and other companies have put in to vastly improve base large language models. Fundamentally, large language models like ChatGPT takes in text input as prompt and then generates text output as its response. Large language models are models that have hundreds of billions or trillions of token parameters and learn from terabytes of data to be able to generate human-like text. Large language model can be engaged in a wide range of text generation tasks, from answering questions to writing essays. So why large language models useful? So before the introduction of large language model, previously we have other small language models. Before the large language model era, each language model can only focus on a single task. For instance, if we want to translate English to German, we have to train a single translation language model to perform this single task. If you want to translate English to Chinese, then that will be another language model. Likewise, if we want to do some text classification, we will need to train a separate model. And if we want a language model to do some regression task, like calculating the similarity between two sentences, that will be a separate model. And finally, if we want to summarize a long paragraph, we will need to train a summarization language model. And before the large language models, small language model couldn't do summarization very well because the outputs are generally not human. It may have a lot of grammatical errors, or some of the sentences may or may not make sense. With the introduction of large language models, nowadays we can have a single model that handles all the tasks. When we open ChatGPT, we can just use the chat interface and key in everything we want ChatGPT to do. And ChatGPT will try its best to help us solve our problems. And the fundamental building blocks of the text inputs is called tokens. So when you read articles about large language models, you should see these tokens very often. So tokens are the basic units of text that the model processes, which can be words, can be part of words, or even punctuations. If you look at this very simple sentence, my favorite color is red. Here, every color coded part of text is considered a token. So you can see here, the my is a token, and favorites with the trailing space is a token, and the space color is a token, and so on. And lastly, the full stop is also a token. For every language model, there will be token limits of the length of input or output text it can process. The better the model, the longer the input's context length it can be. So say for Google Gemini, it can take in up to 2 million tokens worth of inputs, which is very amazing. For ChatGPT or GPT-5, I think the context window is only up to 400,000 tokens. So for some very complex task, when we do vibe coding or when we want to pass in a long string of knowledge, Gemini is able to process a much larger context window than ChatGPT. We know that for a large language models, it takes in text input and then generates a text output. The text inputs are commonly called prompts in the large language model process. So a prompt is essentially this text input. And also another fancy term we call prompt engineering. It is essentially the skills of crafting effective input messages so that the large language model can better understand our intent and generate a more effective response that is of what we want. Now that we have some understanding of the basic terminology, so now let's take a look at how large language model works. So you already learned, if you have gone through the machine learning course, you should know that machine learning broadly categorized into these three categories, namely supervised learning, unsupervised learning, and reinforcement learning. And the common large language model apps that you are familiar, such as ChatGPT, Cloud, Gemini, and Meta AI, they are all under the umbrella of generative models. And here we can see that these generative model fall in conjunction of all these three categories. And that is because the process of training such model needs different stages of training, and they all involve different training processes for different stage. So we can't simply put the large language model or generative model under any single umbrella. Although nowadays, when people, especially non-computer scientists, they talk about AI, they often refer AI as large language models, but AI actually cover much wider spectrum. And we should know that generative models or large language models are a subset of machine learning, which is also a subset of AI. Now let's look at what supervised learning is. So supervised learning typically focuses on creating models that learn patterns from data. The data typically comes with labels like the ground truth answers. So here, this is an illustration of two very simple supervised learning tasks. So we are given some data of some shapes or some color, and we try to train two different models. One we call it classification model, and the other we call it regression model. So when we pass all these observations or this data into the classification model, we expect the model to generate an output that discrete, non-continuous, such as the type of the image. So here the model may guess this green color shape is an apple, and it will guess this pink color shape to be a strawberry. In another regression model, this model may generate continuous outputs, like here the number of items in a given example. So here, if we pass all these into the regression model, the model may guess at least 8.0 units of items within this set of items given. So these two are the most common types of supervised learning models. In the case of unsupervised learning, it focuses on training models that automatically split data into groups with some latent patterns, that is patterns that are not obvious or is hidden from common users. And this kind of data typically comes without label. The model is expected to find the pattern using some algorithm. So using the same example, so the model is given a group of shapes randomly scattered around the space. And when this data is given to the model, will try to find a clear line that separates the different kinds of data points. And then using these fine lines, it tells us at what conditions it will classify which data points into which type. So here, after the clustering, it will tell us this group of items very different from this group of items. But this model couldn't tell us what exactly this item is typically. And finally, for reinforcement learning, it it is commonly trained by providing rewards to correct actions. This is an incentivization model rather than true force model. Reinforcement learning models tend to learn to maximize the rewards by making the right decisions at different scenario. And the data typically comes with labels for correct actions rather than correct answers. Using the same example, we put all these observations together as an environment. And when this machine learning model sees an example, it will take action on something, right? So if let's say the action space, like the sets of actions this model can do, let's say there are two. So one is to guess strawberry, the other is to guess apple. So if this model observe these inputs and decide to take the action of guessing strawberry, this model will be rewarded, say, 100 points. And in another case, this observation is this shape, and this shape is passed into the reinforcement learning model, and the model decide to guess it's a strawberry. Then, given this observation and the action, this model will be penalized with minus 10 marks. And this will be backpropagated to the model to tell the model that, hey, given this observation, you make these actions, and here is your rewards or penalty. Then the model will update itself and try to make better guesses the next time it sees other examples. This is generally the process of reinforcement learning. Sometimes this can be very confusing as compared to supervised learning, because sometimes we are confused with the outputs of reinforcement learning being the rewards, like being the points, and the supervised learning being the, say, labels or some continuous numbers. But I won't go into further detail because that is not the focus of this course, and you all should be an expert after finishing your machine learning modules at the previous trimester. So now let's take a look at linear regression. In the simplest form, we should learn this in secondary school linear algebra. If not your first year trimester, you should know the simplest form of linear regression will be some function of variable x, and the simplest form will be ax plus b, where a and b are called the parameters of x, or of this function. And this function, given a certain number of x, will give us the answer, the calculated answer, which is y. And sometimes y and fx, we will use it interchangeably. If we put these mathematical representations back to linear algebra, the observations here, or the data points here, are what we call x, basically this x. And then the machine learning model, or a regression model, is the function here. So this is the f. And when we take an example and pass into this function, we will get an answer. Either it's calculated or it's predicted or approximated. And this, we will call it either y or fx. Essentially, these are the outputs of this model given an x example. Now let's superposition this model into large language models. In the case of large language models, the number of parameters are not just two, but it can go to hundreds of billions or even trillions. For instance, the largest open source model, DeepSeek R1, is reportedly having 671 billion parameters, and Llama 4 has 2 trillion parameters in total, but it uses this MOE architecture. So at each point of time when it does inference, it will activate 288 billion active parameters. And it's believed that GPT-5 or Gemini 2.5 Pro will have over 2 trillion parameters, although they would never tell us how many parameters they use. And models with fewer than 10 billion parameters, nowadays called small language models, which is very different from earlier what we mentioned, small language models. Last time when we use small language model, it only contained at maybe 20 or 200 million parameters, which is very tiny. It can be run on our computer or our laptop in split seconds. And this inferencing model here, we see the large language model here is essentially the F, and the text here is the X. the prompt is the X, and the output of the model given some example X will be probability distribution of what are the most likely outputs of this fx. So now let's move further than having one output, having one step. Just now we see that these are the X, right? The inputs, and then here there's a large language model F, and when we pass the X into F, we will get a probability distribution of the most likely next token, which is the fx or the y. Fundamentally, a large language model generates text auto-regressively, which means it predicts the next text one by one, rather than either retrieving or generating all the text at the same time. Here, if let's say our prompt starts with the cat, the model will first pick the next word. So here, let's say the model picks is, and the output of this step will will join the inputs and go to the input of next step. The next step, we will have the cat is, which is the original input plus the first step output. And now we pass into the function, the f or the model, and the model is going to generate the next most likely words, which is sitting. And these outputs will join the current inputs, and then it becomes the cat is sitting. And this sitting comes with a full stop, right? So with these 4 tokens, now we pass the X into the model, and the model is going to generate another tree, and then we choose the most likely output, which is a sign to indicate an end of this inference. And then the large language model will choose to end this process. This is an example of autoregressive model or autoregressive next token prediction process. So now let's zoom back into every step. The large language model generates a probability distribution of the next tokens options, right? So here, if we pass in the cat into the model, doesn't generate a single words directly. It will generate this score, this set of scores, which are essentially the probability distribution of all the available tokens in this dictionary. And different large language models may use different tokenization algorithms. So for the tokenization algorithms we used in our lab, it has 262,000 tokens in the dictionary. So here we can see that the word is shows up to have 0.25, which is 25% probability of showing up. And then the next one was has 0.12 and so on. And some token in other languages will show up also. We see Chinese and some other languages. By that, then we choose a word based on the probability distribution. That is how each step works. Here, if let's say we do this process, why the output of the large language model should always be the same, right? Because for every given input, this is function, right? So a function will generate the same set of probability distribution if the token set is the same. Then how come LLMs don't generate response consistently? Every time we pass in the same question, the same input, the same large language model will definitely generate different sets of response, although the main idea can be similar, but the text will be different. How come it doesn't generate the same response? If we take the naive approach, which we let the large language model only choose the token with the highest probability, we will definitely get the answer consistently. That means every time we pass the same input to the model, we will get the same output. That is we only choose the top one token with the highest probability. But oftentimes we don't do that because the most likely next token does not necessarily reflect what the user actually wants. So our models, the large language model apps, tend to use different scheme to do the generation. The second approach that is potentially better or more robust than the top one approach is to roll a dice, right? So this dice has 262,000 faces rather than six faces, and the probability of landing at each face will be according to the probability distribution that is corresponding to all these tokens, right? So now we we have the cat as input, we pass to the language model, the model generates a probability distribution, and then we roll these dice, and then we will take the input realistically. So now every token has some chance to show up instead of only the top one. This is the second approach. But now, if you look at large language model, the actual LLM apps like ChatGPT, Cloud by Anthropic, and Gemini, when we pass in the cats, the way they are answered very differently, right? So here, ChatGPT asks us, can you clarify what you mean by the cat? Are you asking about a specific cat or phrase or something else? As of Cloud, if you mention what we ask, I see you mentioned the cat, and are you thinking about a particular cat, or would you like to talk about cats in general? And here in Gemini, same thing. It asks for further clarification and also suggest some specific things that maybe we actually want. Here we see that now large language model apps actually try to guess what we want, what the user intent is, rather than directly do the next token inferencing or next token generation. And this happened because of this notion of prompt engineering, right? Although we, as a user, we pass in the cat into the large language model, ChatGPT or other LLM apps actually enhance the inputs by putting in a lot of other instructions wrapping around the inputs we have. So before the text actually go into GPT, ChatGPT will put some overarching prompts. We call it system prompt. So first, it will add instructions saying that you are a helpful assistant. And then before the user prompt, it will add user ask, colon, and the whatever we put in, and with full stop. And then the the next time we will say you answer, colon. And so this will be the actual text that will be passed into ChatGPT, and ChatGPT will then look at the whole text and generate. That's why when we actually pass in very abstract inputs to ChatGPT or to other LLM apps, it doesn't give us a direct inference or the next token inferencing repeatedly. Now that we know how large language model works, right, by continuously guessing the next tokens repeatedly, we should know that we should be able to understand that LLMs are bad at mathematics by default. And the reason being is that large language model generates the response token by token, right? So here, if we just put in a very simple mathematical equation like 34 times 6 into a tool or into some algorithm, we can easily get some deterministic response that is always correct if the task is not too difficult. But if we pass the same thing to a large language model, the large language model will do the autoregressive inferencing by generating distribution of probability distribution of all the possible outputs, which includes the 10 digits as well as all other natural language tokens in different languages. And then it will roll a dice and then see which are the most likely next token. So there's a chance that the most likely token doesn't come out. If the equation is very simple, chances are by guessing the most likely next token, it can still get the answers correctly. But when the math equation gets longer, large language models tend to make mistakes more and more likely. For instance, for here, if it's a 6-digit by 6-digit multiplication, and if so this will generate an 11-digit numbers. That means the large language model will need to guess 11 times. If let's say for every next token, it gets 99%, the next token's probability is 99%. And if we guess it for 11 times at 99% accuracy, we will get 0.895% accuracy probability of getting everything correct. And given that we will have 10%, over 10% chance of getting it wrong, as compared to using a calculator, right? A calculator will almost always get it correctly. To solve this problem, large language models are taught to do more advanced tasks. For instance, using tools. Instead of giving the inputs to a large language model and generates the output by probability distribution autoregressively, large language model will detect that this task actually requires some external help, and then it will call the tool, it will call the suitable tool to perform some deterministic task, and then the output of this tool will be passed back to the large language model, and the large language model will use this as context or as reference to generate the output. By simply using tool, large language model will be able to solve mathematic or other logical tasks in much more accurately than direct inferencing. With harder problems, large language models will trigger more advanced tools. Here, I would like to introduce this practice called program assisted or program aided language model, or PAL, which we very commonly see it in ChatGPT nowadays. When we ask a difficult task, it will first think about whether this task needs to use tool or it can be answered directly. And if it thinks that this task is hard enough, it will write a script, most often a Python script, and then execute the script to get the answer, and then use this answer to generate the response. And here, it will even take a further step to validate if this answer is correct by doing some logical inferencing or formally chain of thoughts to check if the answer makes sense for the requested task. And after that, it will then process the entire chain of thoughts into human readable output text and feedback to the user. And with this PAL or PAL, ChatGPT is able to solve complex tasks with very high accuracy. So now let's take a look at what is beyond language. Before we talk about other models that is beyond language, we need to know something about data. We have seen this term data on a daily basis. Everywhere we talk about data, but what data actually is. So without going into too much detail, I want to mention this notion about modalities. Modalities is essentially different forms that data is represented or presented to you, right? So these are the most common kinds of modalities, right? We have text. Okay, text, we see natural language. That means the textual information that comes with its own meaning, it comes with semantics, and it can be in different languages like English or Chinese or Spanish or other languages. Right, so these are the most common textual data. We also have other kind of textual data, and we group them as this notion of formal languages. Here we see this is a textual representation of logic or a very simple algorithm. Okay, this algorithm takes there's some variable, some number assignment to the variable, and then there is some conditional operations. So if a condition happen, then perform some task, else we go into an inner if else, and then it ends, like the procedure ends. So this is textual representation of logic. We also have textual representation of formula or functions, right? Functions are essentially an abstract form of representing some observation, right? Some physics, some physical conclusion or theorem, right? So here, although it's represented by text, each letter or each symbol has its own preset meaning that requires lots of prior knowledge. Without prior knowledge, let's say if we look at the transfer function without revising what we learned for physics, we probably don't understand what it's saying here, right? But if large language model learns all those contexts, and when it reads all this formula in this shape, in this form, it will understand something that may otherwise need to be written in 3,000 tokens in natural language. Here we see SQL query. SQL query, similarly to programming language or similarly to logic, there are some specific keywords that takes higher priority. Say creates, right? Select from where. All these are specific keywords that this formal language, i.e. SQL, reserved. And there are human or there are users defined content, say CS underscore SCL1 or customer underscore stream. These are user defined terms like age or some 25, like all these are user given. In a system of formal language, there are text or textual information of different priorities, which is different from the form of natural language, right? For natural language, given the same language like English, the words doesn't have any priorities. All the text has its own meaning, but at the same priority. Okay, so this is also another form of textual representation. And finally, this is like source code that we deal with on a daily basis, right? So source code is similar to a SQL we see here. And for some scope like function, it processes some information like logic, right? So this is also another form of formal language. For visual, we commonly see images, right? So there can be photos, it can be painting, it can be charts and diagrams. I didn't put all those examples, but actually they are very different visual representation, although they are under the umbrella of visual modality. We also have a very special kind of visual representation, which is video. If we think about what actually a video is, so first, video is moving pictures, right? It's a stack of pictures moving in some time interval. Okay, and a video process more information than a simply collection of images, right? Because inside a video, there are multiple objects, and each object has its like a video records the evolution of the object, right? Let's say the transitioning, the change of size, and the change of states. Like let's say there's a monkey that walks from far and then showing its teeth at a certain seconds. So a video is formed by a sequence of images, but it contains a lot more information than merely a stack of images. And video also process audio. So audio and the combination of the moving pictures and the time series audio data process some information that it can be studied also. Video is another special type of visual representation. And finally, we have audio, right? So audio is commonly time series dataset. That means it can be represented by X and Y, two axes, where X is the time series. So it can be by seconds or milliseconds or month or year. And the Y can be the volume, it can be the frequency, right? Depending on what we want to record. And the type of audio contents contain, say, speech. which have some semantics to it. This speech can be converted to transcript that goes back to natural language. It also processes some emotional content, sentiment content. It also can process some implication, like say humor or sarcasm, or maybe some other political intent. We never know. And the second type of audio is music, right? So we are very familiar. So when we study, when we run, when we do other things, we are exposed to music. So music doesn't have its semantics, but also process some emotional content, right? And it has a clear pattern, right? And it's represented by small faces. And finally, there are natural sounds, right? Like here it shows a thunder, right? So the thunder process a sequence of sound that help us classify what the type is. Or if we walk into a forest, we hear a combination of many natural sounds, that maybe there is water flowing, there's wind, there's leaves that hitting each other, and there are some insects sound. Right? So all these natural sounds that processes some patterns but doesn't process semantics typically. These are some information about data. So now, why do we mention that, right? So now that we know data exceeds beyond text, we take a step further to look at large language models. So large language models, after it's first introduced, now they extended to other modalities, right? It's extended to process other form of data, right? So the original form is text to text, right? It takes in text and generate text. And later, ChatGPT takes in text and draw something for us, right? And also, it can take in a text and then write a song or write some melody clips for us, right? So nowadays, large language models, or more commonly known as foundation models, is able to take in text and generates beyond text. It can generate images, it can generate audios, it can also generate like videos and so on. How about the inputs? So just now it takes in a text prompt and generate an image. And we can also do image plus text to generate image plus text. So here, instead of asking ChatGPT to directly generate a Mona Lisa to a Japanese anime style, we can pass in the original Mona Lisa or a photo of our own and ask ChatGPT to change our own photo to a Japanese anime style. And ChatGPT will then help us generate the image, and sometimes it comes with some description saying that here is a Mona Lisa in Japanese anime style, right? And to take a step further, ChatGPT can also generate some videos for us, or VO by Gemini, which is very powerful. If we pass in an image and pass in some music or some melody, some MIDI, ChatGPT or large language models can generate some fancy video for us. Of course, we can pass in other things like textual information, like a prompt to specify what we want the model to generate. Here we see some examples of cross-modal generation or multi-modal generation, where the inputs and outputs process different modalities, and the large language model in the process can handle data that is a combination of more than one modality, more than one data type. And the way to do that is very simple, right? So we have seen that the large language model breaks like the text into specific tokens as inputs. Large language model can also break different modalities into tokens, right? Here, for instance, for Mona Lisa, this image is broken into many small patches, right? Each patch can be 16 by 16, although the scale is not very correct, but you just imagine this is a square, right? It's a 16 by 16 pixels patch, and each patch has three channels, either HSV or RGB, right? So it's 16 by 16 by 3 tensor, and this box is a token that is taken out from original image, right? So the model breaks the inputs into textual tokens and also visual tokens. And then together it generates the image token by token. And then it merge it or it decode it into the complete image. For audio also, it works similarly, right? So it takes in some text tokens, and when it generates audio signals, it takes, let's say, 0.2 seconds clip as a token, and then it auto-regressive generates the next 0.2 and next 0.2 repeatedly. This 0.2 seconds after the being generated, it will be moved into here to generate the next 0.2 seconds of token, right? And then it repeats until a specific ending sign is shown. To allow cross-modal or multi-modal generation, tokenization, the accuracy of tokenization could be the key. Can we extend it to even further? So now here is the video of a launch of Generative by Gemini. Let's watch a video here. So here we see that nowadays, for a foundation model or a large language model, it can generate from anything to anything with proper tokenization. So given any kind of modality, say for text, for images, for audio, or for any others, right? So as long as we find a way that properly tokenize the input into all these X, and then we pass all these into a large enough or smart enough model, the model will be able to generate the tokens auto-regressively, right? And as long as the tokenization is accurate, we can decode it into any forms, right? So not just now we see that the world model is fundamentally formed by text and image and audio, right? Just that it's of a much larger scale, right? It's in a real-time continuous generation of images and maybe background audio and maybe some of the textual input. And you can inject prompt while it's generating the next frame. It's a pretty amazing kind of demo, a pretty amazing kind of experience, but fundamentally works the same as how originally large language model works, which is just guessing the next token auto-regressively. Here we can see the auto-regressive generation process, right? So taken these inputs, it will generate the first token, and then it will generate the second token, and so on. And then given some proper decoding process, we are able to form the outputs either in a separate form, like how we see in ChatGPT, or in a very complex, cohesive form, like we see in the Genie video. Now we enter the last part. So I want to give you guys a very brief overview of the differences between AI models and AI agents. We already know just now that large language models are auto-regressive text generator, that it takes in some text input and then it generates some text output. And the process is by guessing the next, like most likely token repeatedly, right? Auto-regressively. But an AI agents does more than that. So beyond taking text inputs and generates text outputs, the key difference between an AI agent and an AI model is that an agent can execute for us also. It can take action. A large language model, like let's say ChatGPT, we ask it a question and it answers for us. An agent can actually do things for us. Let's say we can ask it to help us send an email, or we can ask it to write a piece of code and execute for us, or we can ask it to control some of the vehicles, for instance. Things that this agent can take actions. And in the process, an agent needs to understand the text query, the prompt, and needs to be able to plan how to do it properly, and needs to know the quality or the states of the planning. And these are handled by this planning or reasoning model, which is essentially a language model, but specifically fine-tuned or post-trained to handle long sequence reasoning task. That means a task that takes a long thought process to do. It also have to understand or judge how well the task is performed and at what stage it should move on to the next stage or recurse back to the previous stage to make some correction. And once some task is done, we will need to update some memory, right? So the memory can be some in a contextual form, like in a database where some knowledge corresponding to the prompt we should know. It can also be in real-time information that we curate from the internet or from sources of data, right? So these are the memory mechanism. And we also need to have a set of tools that are well developed and exposed to the agent or to the reasoning model, that the model knows what are the capabilities of the agent and when it can call the correct tool to do the correct job. These are the main components that enable an agent to do some execution for us. Now that we have a sense of what is the difference between a large language model and an AI agent, so now I want to ask you guys, what do you think if ChatGPT is a model or an agent? Thank you for your attention.